And you're live.
Okay, hello everyone. Well, let's see. Today we're going to try a bit of an experiment. There is a piece that I wrote a couple of weeks ago about charting a course for complexity. And we've been keen to turn some of these pieces that I write into podcasts. Some of them work better than others. Some of them are full of ornate pictures, which can't really be described very well in words. Others are more word-oriented. This is one of the more word-oriented pieces I've written recently. So what I'm going to do here is I'm basically going to read this piece, and that will turn into a podcast. And then I am happy to take questions and do Q&A. And the way I'd like to point out that tomorrow afternoon, we'll be doing a Q&A about our physics project. Today, the Q&A will be about what's in this piece, which is called Charting a Course for Complexity. So without further ado, let me go ahead and try and tell you what this piece said. And for my team, hopefully, if I trip up horribly, you should note the time so we can edit that so we have a perfect podcast from this. Okay. All right. So here goes. So I'm going to be going through a piece that I wrote called Charting a Course for Complexity, Metamodeling, Ruleology, and More. So this piece is the first of a series that I'm planning to write in connection with the upcoming 20th anniversary of the publication of my big book, A New Kind of Science, in 2002. First section, there's a whole new field to build. For me, the story began nearly 50 years ago as what I saw as a great and fundamental mystery of science. We see all sorts of complexity in nature and elsewhere, but where does it come from? How is it made? There are many examples: snowflakes, galaxies, life forms, turbulence. Do they all work differently? Or was there some common underlying cause, some essential phenomenon of complexity? It was 1980 when I began to seriously work on these questions. And at first I did so in the main scientific paradigm I knew, models based on mathematics and mathematical equations. I studied the approaches people had tried to use: non-equilibrium thermodynamics, synergetics, nonlinear dynamics, cybernetics, general systems theory. I imagined that the key question was, starting from disorder and randomness, how could spontaneous self-organization occur to produce the complexity we see? For somehow I assumed that complexity must be created as a kind of filtering of ubiquitous thermodynamic-like randomness in the world. At first, I didn't get very far. I could write down equations and do math, but there wasn't any real complexity in sight. But in a quirk of history that I now realize had tremendous significance, I had just spent a couple of years creating a big computer system that was ultimately a direct forerunner of our modern Wolfram language. So for me, it was obvious. If I couldn't figure out things for myself with math, I should use a computer. And there was something else. The computer system I'd built was a language that I'd realized, in a nod to my experience with reductionist physical science, will be the most powerful if it could be based on principles and primitives that were as minimal as possible. And that had worked out very well for the language. And so when it came to complexity, it was natural to try to do the same thing and to try to find the most minimal, most meta kind of model to use. I didn't know just what magic ingredients I'd need in order to get complexity, but I thought I might as well start absolutely as simple as possible. And so it was that I set about running programs that I later learned were a simplified version of what had been called cellular automata before. I don't think it was even an hour before I realized that something very interesting was going on. I'd start from randomness, and spontaneously, the programs would generate all sorts of complex patterns. At first, it was experimental work. I'd make observations, cataloging and classifying what I saw, but soon I brought in analysis tools from statistical mechanics, dynamical systems theory, statistics, wherever. And I figured out all sorts of things. But at the center of everything, there was still a crucial question. What was the essence of what I was seeing? And how did it connect to existing science? I wanted to simplify still further. What if I didn't start from randomness, but instead started from the simplest possible seed? There were immediately patterns like fractals, but somehow I just assumed that a simple program with simple rules starting from a simple seed just didn't have what it took to make true complexity. I'd had printouts, yes, that was how it worked back then, that showed this wasn't true, but for a couple of years, I somehow ignored them. Then in 1984, I made my first high-resolution picture of Rule 30. And I now couldn't get away from it. A simple rule and a simple seed were making something that seemed extremely complex. But was it really that complex? Or was there some magic method of analysis that would immediately crack it? For months, I looked for one from mathematics, mathematical physics, computation theory, cryptography, but I found nothing. And slowly it began to dawn on me that I'd been fundamentally wrong in my basic intuition, and that in the world of simple programs, or at least cellular automata, complexity was actually easy to make. Could it really be that this was the secret that nature had been using all along to make complexity? I began to think it was at least a big part of it. I started to make connections to specific examples in crystal growth, fluid flow, biological forms, and other places. But I also wanted to understand the fundamental principles of what was going on. Simple programs could produce complex behavior, but why? It wasn't long before I realized something fundamental, that this was at its core a computational phenomenon. It wasn't something one could readily see with math. It required a different way of thinking about things, a fundamentally computational way. At first, I had imagined that having a program as a model of something was essentially just a convenience. But I realized that it wasn't. I realized that computational models were something fundamentally new with their own conceptual framework, character, and intuition. And as an example of that, I realized that they showed a new central phenomenon that I called computational irreducibility. For several centuries, the tradition and aspiration of exact science had been to predict numbers that would say what a system would do. But what I realized is that in most of the computational universe of simple programs, you can't do that. Even if you know the rules for a system, you may still have to do an irreducible amount of computational work to figure out what it will do. And that's why its behavior will seem complex. By 1985, I knew these things, and I was tremendously excited about their implications. I'd got to this point by trying to solve the problem of complexity, and it seemed only natural to label what could now be done as complex systems theory, a theory of systems that show complexity even from simple rules. And so it was that in 1985, I began to promote the idea of a new field of complex systems research, or for short, complexity, fueled by discoveries that I'd made about things like cellular automata. Now that I know more about history, I realized that the thrust of what I wanted to do had definite precursors, especially from the 1950s. For that was a time when the concepts of computing were first being worked out, and through approaches like cybernetics and the nascent area of artificial intelligence, people started exploring the broader scientific implications of computational ideas. But with no inkling of the phenomena I discovered decades later, this didn't seem terribly promising, and the effort was largely abandoned. By the late 1970s, though, there were other initiatives emerging, particularly coming from mathematics and mathematical physics. Among them were fractals, catastrophe theory, and chaos theory. Each in a different way explored some form of complexity, but all of them in a sense operated largely in the comfort of traditional mathematical ideas. And while they used computers as practical tools, they never made the jump to seeing computation as a core paradigm for thinking about science. So what became of the complex systems research I championed in 1985? It's been 36 years now. Careers have come and gone, several academic generations have passed by. Some things have developed well, some things have not developed so well. But I, for one, know much more than I did then. For me, my work in the early 1980s was a foundation for the whole tower of science and technology that I've spent my life since then building, most recently culminating in our Wolfram physics project, and what in just the past few weeks, I've called the Multi-Computational Paradigm. Nothing I've learned in these 36 years has dulled the strength and beauty of Rule 30 and those early discoveries about complexity, but I now have so much more context and a so much bigger conceptual framework from which it's possible to see so much more about complexity and about its place and potential in science. Back in 1985, I was pretty much a lone voice expressing the potential for studying complexity in science. Now there are perhaps 1,000 scientific institutes around the world nominally focused on complexity. And my goal here is to share what I've learned and figured out about what it's now possible to do under the banner of complexity. There are exciting and surprising things. Some I was already beginning to think about in the 1980s, but others have only come into focus or even become conceivable as a result of very recent progress around our physics project and the formalism it has developed. The emergence of a new kind of science. Back in 1985, I was tremendously excited about the potential for developing the field of complex systems research. It seemed as if there was a vast new domain that had suddenly been made accessible to scientific exploration. And in it, I could see so much great science that could be done and so many wonderful opportunities for so many people. I myself was only 25 years old, but I had some organizational experience, both leading a research group and starting my first company. And I set about applying what I knew to complex systems research. By the following year, I'd founded the first research center and the first journal in the field, Complex Systems, which is still going strong after 35 years. And had also done things like suggesting complexity as the theme for what became the Santa Fe Institute. But somehow everything moved very slowly. Despite my efforts, complex systems research wasn't a thing yet. It wasn't something universities were teaching. It wasn't something that was a category for funding. There was some applications of the field emerging, and there was tremendous pressure, particularly in the context of those applications, to shoehorn it into some existing area. Yes, it might have to take on the methodology of its host area, but at least it would have a home. But it really wasn't physics, or computer science, or math, or biology, or economics, or any known field. At least as I envisioned it, it was its own thing with its own new emerging methodology. And that was what I really thought should be developed. I was impatient to see that happen. I was impatient to have it happen. And by late 1986, I decided the best path was just to try to do it myself and to set up the best tools and best environment for that. The result was Mathematica, and now the Wolfram language, as well as Wolfram research. And for a few years, the task of creating these entirely consumed me. But in 1991, I returned to the basic science. But in 1991, I returned to basic science and set about continuing where I had left off 5 years earlier. It was an exciting time. I quickly found that the phenomena I had discovered in cellular automata were quite general. I explored all sorts of different kinds of rules and programs, always trying to understand the essence of what they were doing. But every time, the core phenomena I found were the same. Computational irreducibility, as unexpected as it had been when I first saw it in cellular automata, was everywhere. And I soon realized that beneath what I was seeing, there was a deep and general principle that I call the principle of computational equivalence that I now consider to be one of the most fundamental things we know about the computational universe. But what did these discoveries about simple programs in the computational universe apply to? My initial target had been immediately observable phenomena in the natural world. And I had somehow assumed that ideas like evolutionary adaptation or mathematical proof would be outside the domain. But as the years went by, I realized that the force of computational equivalence was much greater than I'd ever imagined, and that it encompassed these things too. I spent the 1990s exploring the computational universe and its applications and steadily writing a book about what I was discovering. At first, in recognition of my original objective, I called the book A Science of Complexity. But by the mid-1990s, I had realized that what I was doing far transcended the specific goal of understanding the phenomenon of complexity. Instead, the core of what I was doing was to introduce a whole new kind of science based on a new paradigm, essentially what I would now call the paradigm of computation. For 3 centuries, theoretical science had been dominated by the idea of using mathematical equations to describe the world. But now there was a new idea, the idea not of solving equations, but instead of setting up computational rules that could be explicitly run to represent and reproduce things in the world. For 3 centuries, theoretical models have been based on the fairly narrow set of constructs provided by mathematical equations, and particularly calculus. But now the whole computational universe of possible programs and possible rules was opened up as a source of raw material for making models. But with this new power came a sobering realization. Out in the unrestricted computational universe, computational irreducibility is everywhere. So yes, there was now a way to create models for many things, but to figure out the consequences of those models might take irreducible computational work. Without the computational paradigm, systems that showed significant complexity had seemed quite inaccessible to science. But now there was an underlying way to model them and to successfully reproduce the complexity of their behavior. but computational irreducibility was all over them, fundamentally limiting what could be predicted or understood about how they behave. For more than a decade, I worked through the implications of these ideas, continually surprised at how many foundational questions across all sorts of fields they seem to address. And particularly given the tools and technology I developed, I think I became pretty efficient at the research I did. And finally, in 2002, I decided I'd pretty much picked all the low-hanging fruit, and it was time to publish my Magnum Opus, titled after what I consider to be its main intellectual thrust, A New Kind of Science. The book was a mixture of pure basic science about simple programs and what they do, together with a discussion of principles deduced from studying these programs, as well as applications to specific fields. If the original question had been, where does complexity come from? I felt I'd basically nailed that. And the book was now an exploration of what one could do in a science where the emergence of complexity from simplicity was just a feature of the deeper idea of introducing the computational paradigm as a foundation for a new kind of science. I put tremendous effort into making the exposition in the book in both words and pictures as clear as possible and contextualizing it with extensive historical research. And in general, all this effort paid off excellently, allowing the message of the book to reach a very wide audience. What did people take away from the book? Some were confused by its new paradigm. Where are all the equations, they asked. Some saw it as a somewhat mysterious wellspring of new forms and structures. Those are great pictures, they said. But what many people saw in it was 1,000 pages of evidence that simple programs and computational rules could be a rich and successful source of models and ideas for science. It's hard to trace the exact chains of influence, but in the past 2 decades, there's been a remarkable, if somewhat silent, transformation. For 300 years, serious models in science had essentially always been based on mathematical equations. But in the short space of just 20 years, that's all changed. And now the vast majority of new models are based not on equations, but on programs. It's a dramatic and important paradigmatic change whose implications are just beginning to be felt. But what of complexity? In the past, it was always a challenge to get complexity out of a model. Now with computational models, it tends to be very easy. Complexity has gone from something mysterious and out of reach to something ubiquitous and commonplace. But what has that meant for the study of complexity? Well, that's a story with quite some complexity to it. The growth of complexity. From 1984 to 1986, I put great effort into presenting and promoting the idea of complex systems research. But by the time I basically left the field in 1986 to concentrate on technology for a few years, I hadn't seen much traction for the idea. A decade later, however, the story was quite different. I myself was quietly working away on what will become a new kind of science, but elsewhere it seemed like my marketing message for complexity had firmly taken root, and there were complexity institutes starting to pop up all over the place. What did people even mean by complexity? It often seemed to mean different things to different people. Sometimes it just meant stuff in our field we haven't figured out yet. More often it meant stuff that seems fundamental, but we haven't been able to figure it out. Pretty often there was some visualization component. Look at how complex this plot seems. But whatever exactly it might mean to different people, complexity was unquestionably becoming a popular science brand, and there were plenty of people eager to affiliate with it, at the very least to give the work they've been doing for years a new air of modernity. And while it was easy to be cynical about some of this, it had one very important positive consequence. Complexity became a kind of banner for interdisciplinary work. As science had gotten bigger and more institutionalized, it inevitably became more siloed, with people in different departments at the same university routinely never even having met. But now people from all kinds of fields could say, yes, we run into complexity in our field, and with complexity as a banner, they now had a reason to connect and maybe even a reason to form an institute together. So what actually got done? Some of it I might summarize as, yes, it's complex, but we can find something mathematical in it, with the typical notion being the pursuit of some kind of power law formula. But the more important strand has been one that starts to actually take the computational paradigm on board, with the thrust typically being, we can write a program to reproduce what we're looking at. And one of the great feelings of power has been that even in fields like the social sciences, where there really haven't been much more than verbal models before, it's now appeared possible to get models that at least seem much more scientific. Sometimes the models have been purely empirical. Look, there's a power law. Sometimes they've been based on constructing programs to reproduce behavior. The definition of success has often been a bit questionable, however. Yes, there's a program that shows some features of whatever system one's looking at, but how complicated is the program? How much of what's coming out is basically just being put right into the program? For mathematical models, people have long had familiarity with questions like, how many parameters does that model have? But when it comes to programs, there's been a tendency just to put more and more into them without doing much accounting of it. And then there's the matter of complexity. Let's say whatever one's trying to model shows complexity. Then often the thinking seems to be that to get that complexity out, there needs to somehow have enough have been enough complexity in the model. And when complexity does manage to come out, there's a feeling that this is some kind of triumph and evidence that the model is on the right track. But actually, as I discovered in studying the computational universe of simple programs, this really isn't the right intuition at all, because it fundamentally doesn't take into account computational irreducibility. And knowing that computational irreducibility is ubiquitous, we know that complexity is too. It's not something special and on the right track that's making a model produce complexity. Instead, producing complexity is just something a very wide range of computational models naturally do. Still, the general field and brand of complexity continued to gain traction. Back in 1986, my complex systems journal had been the only one devoted to complex systems research. By the late 2010s, there were dozens of journals in the field, and my original efforts from the 1980s to promote the study of complexity have been thoroughly dwarfed by a whole complexity institute, a whole complexity industry that had grown up. But looking at what's been done, I feel like there's something important that's missing. Yes, it's wonderful that there's been so much complexity activity, but it feels scattered and incoherent and without a strong common thread. Returning to the foundations of complexity. There's a vast amount that's now been done under the banner of complexity, but how does it fit together? And what are its intellectual underpinnings? The dynamics of academia has left most of the ongoing activity of complexity research to be about specific applications in specific fields, and not really to concern itself with what basic science might lie underneath and what the foundations of complexity might be. But the great power of basic science is the economy of scale it brings. Find one principle of basic science and it can inform a vast range of different specific applications that would otherwise each have to be explored on their own. Learn one principle of basic science and you immediately know something that subsumes all sorts of particular things you would otherwise separately have to learn. So what about complexity? Is there something underneath all those specifics that one can view as a coherent basic science of complexity, and for example, the raw material for something like a course on foundations of complexity? At first, it might not be obvious where to look for this, but there's immediately a big clue. What is in a sense the biggest meta discovery of the study of complexity of the past few decades, that across all kinds of systems, computational models work. So then one's led to the question of what the basic science of computational models or computational systems in general might be. But that's precisely what my work on the computational universe of simple programs and my book, A New Kind of Science, are about. They're about the core basic science of the computational universe and the principle that involves, in a sense, the foundational science of computation. It's important, by the way, to distinguish this from computer science. Computer science is about programs and computations that we humans construct for certain purposes. But the foundational science we need is instead about programs and computations in the wild and about what's out there in general in the computational universe, independent of whether we humans would have a reason to construct or use it. It's a very abstract kind of thing that, like pure mathematics, can be studied completely on its own without reference to any particular application. And in fact, the analogy to pure mathematics is an apt one, because just as pure mathematics is in a sense the abstract underpinning for the mathematical sciences and the whole mathematical paradigm for representing the world, so now our foundational science of computation is the abstract underpinning for the computational paradigm for representing the world and for all the computational X fields that flow from it. So yes, there is a core basic science of complexity, and it's also essentially the foundational science of computation. And by studying this, we can bring together all sorts of seemingly disparate issues that arise in the study of complexity in different systems. Everywhere we'll see computational irreducibility. Everywhere we'll see intrinsic randomness generation. Everywhere we'll see the effects of the principle of computational equivalence. These are general abstract things from pure basic science. They're the intellectual underpinnings of the study of complexity, the foundations of complexity. Metamodeling and the meta theory of models. There's a definition at the top. Metamodeling, a noun, the meta science of finding minimal models for models. I was at a complexity conference once talking to somebody who was modeling fish and their behavior. Proudly, the person showed me his simulated fish tank. How many parameters does this involve? I asked. About 90, he said. My gosh, I said, with that many parameters, you could put an elephant in your fish tank too. If one wanted to make a simulated fish tank display just for people to watch, then having all those parameters might be just fine. But it's not so helpful if one wants to understand the science of fish. The fish have different shapes. The fish swim around in different configurations. What are the core things that lead to what we see? To answer that, we have to drill down. We have to find the essence of fish shape or fish behavior. At first, if confronted with complexity, we might say it's hopeless. We'll never find the essence of what's going on. It's all too complicated. But the whole point is that we now know that in the computational universe of possible programs, there can in fact be simple programs with simple rules that lead to immense complexity. So even though there's immense complexity in behavior, we see underneath it can all there can still be something. So even though there's immense complexity in behavior, we see underneath it all, there can still be something simple and understandable. In a sense, the concept of taking phenomena and drilling down to find their underlying essential causes is at the heart of reductionist science. But as this has traditionally been practiced, it's relied on being able to see one's way through this drilling down process, or in effect, to explicitly do reverse engineering. But a big lesson of the computational paradigm is that the phenomenon of computational irreducibility and the irreducible distance that can exist between the rules and behavior they produce. It's a double-edged thing, however. Yes, it's hard to drill down through computational irreducibility, but in the end, the details of what's underneath may not matter so much. The main features one sees may just be generic reflections of the phenomenon of computational irreducibility. Still, there are normally some structural features of the underlying models or in their interpretations that matter for particular applications. Is one dealing with something on a two-dimensional grid? Are there non-local effects in the system? Is there directionality to the states of the system, and so on? If one looks at the literature of complexity, one finds all sorts of models for all sorts of systems. And often, like the fish example, the models are very complicated. But the question is, are there simpler models lurking underneath? Models simple enough that one can readily understand at least their basic rules and structure. Models simple enough that it's plausible that they could be useful for other systems as well. To find such things is in a sense an exercise in what one can call metamodeling, trying to make a model of a model, doing reductionist science not on observations of the world, but on the structure of models. When I first worked on the problem of complexity, one of the main things I did was a piece of metamodeling. I was looking at models for a whole variety of phenomena, from snowflake growth to self-gravitating gases to neural nets. But what I did was to try to identify an underlying meta model that would cover all of them. And what I came up with was simple cellular automata, which, by the way, don't cover everything I've been looking at, but turn out to be very interesting anyway. As I think about it now, I realize that the activity of metamodeling is not a common one in science. In mathematics, one could argue that something like categorification is somewhat analogous. But to me personally, metamodeling has seemed very natural because it's very much like something I've done for a very long time, which is language design. What's involved in language design? You start off from a whole collection of computations and descriptions of how to do them, and then you try to drill down to identify a small set of primitives that let you conveniently build up those computations. Just like metamodeling is about removing all the hairy parts of models to get to their minimal primitive forms, so also language design is about doing that for computations and computational structures. In both cases, there's a certain art to it, because in both cases, the consumers of those minimal models, those minimal forms, are humans. And it's to humans that they need to seem simple and understandable. Some of the practical definition of simplicity has to do with history. What, for example, has become familiar, or are there words for? Some is more about human perception. What can be represented by a diagram that our visual processing system can readily absorb? But once one's found something minimal, the great value of it is that it tends to be very general. Whereas a detailed, hairy model tends to have all sorts of features specific to a particular system, a simple model tends to be applicable to all sorts of systems. So by doing the meta-modeling and finding the simplest common model, one is effectively deriving something that will have the greatest leverage. I've seen this quite dramatically with cellular automata over the past 40 years. Cellular automata are, in a sense, minimal models in which there's a definite, discrete structure for space and time and a finite number of states associated with each discrete cell. And it's been remarkable how many different kinds of systems can successfully be modeled by cellular automata. So that, for example, the 256 very simplest two-color nearest neighbor 1D rules, a significant fraction of these have found applications somewhere, and many have found several often completely different applications. I have to say that I haven't explicitly thought of myself as pursuing meta-modeling in the past, and in fact, I only just invented the term, but I believe it's an important technique and idea, and it's one that can mine the specific modeling achievements of work on complexity and bring them to a broader and more foundational level. In A New Kind of Science, I cataloged and studied minimal kinds of models of many types, and in the 20 years since A New Kind of Science was finished, I've seen only a modest number of new minimal models. I haven't been looking for them with the focus that meta-modeling now brings. But recently, I have another major example of what I now call meta-modeling. For our physics project, we've developed a particular class of models based on multi-way hypergraph rewriting. But I've recently realized that there's meta-modeling to do here, and the result has been the general concept of multi-computation and multi-computational models. Returning to complexity, one can imagine taking all the academic papers in the field and identifying the models they used, and then trying to do meta-modeling to classify and boil down these models. Often I suspect the resulting minimal classes of models will be ones we already have seen, and that, for example, appear in A New Kind of Science. But occasionally they'll be new, in a sense, new primitives for the language of modeling and new meta-scientific output from the study of complexity. The pure basic science of ruleology as a definition. Ruleology, a noun, the pure basic science of what simple rules do. If one sets up a system to follow a particular set of simple rules, what will the system do? Or put another way, how do all those simple programs out there in the computational universe of possible programs behave? These are pure abstract questions of basic science. They're questions one's led to ask when one's operating in the computational paradigm that I describe in A New Kind of Science. But at some level, they're questions about the specific science of what abstract rules that we can describe as programs do. What is that science? It's not computer science, because that will be about programs we construct for particular purposes, rather than ones that are just out there in the wilds of the computational universe. It's not, as such, mathematics, because it's about seeing what rules do, rather than finding frameworks in which things can be proved. And in the end, it's clear it's actually a new science that's rich and broad, and that I at least have had the pleasure of practicing for 40 years. But what should this science be called? I've wondered about this for decades. I've filled so many pages with possible names. Could it be based on Greek or Latin words associated with rules? Those are arch and reg, very well-trafficked roots. What about words associated with computation? Well, that'd be logis or calc. None of those seem to work. But in something akin to the process of meta-modeling, we can ask, what is the essence of what we want to communicate in the word? It's all about studying rules and what their consequences are. So why not the simple and obvious ruleology? Yes, it's a new and slightly unusual sounding word, but I think it does well at communicating what this science that I've enjoyed for so long is about. And I, for one, will be pleased to call myself a ruleologist. But what is ruleology really about? It's a pure basic science and a very clean and precise one. It's about setting up abstract rules and then seeing what they do. There's no wiggle room, no issue with reproducibility. You run a rule and it does what it does, the same every time. What does the Rule 73 cellular automaton starting from a single black cell do? What does some particular Turing machine do? What does some particular multi-way string substitution system do? These are specific questions of ruleology. At first, you might just do the computation and visualize the result, but maybe you notice some particular feature, and then you can use whatever methods it takes to get a specific ruleological result, and to establish, for example, that in the Rule 73 pattern, black cells appear only in odd-length blocks. Ruleology tends to start with specific cases of specific rules, but then it generalizes, looking at broader ranges of cases for a particular rule or whole classes of rules. And it always has the concrete things to do, visualizing behavior, measuring specific features, and so on. But ruleology quickly comes face to face with computational irreducibility. What does some particular case of some particular rule eventually do? That may require an irreducible amount of computational effort to find out. And if one insists on knowing what amounts to a truly general, infinite, truly infinite time result, it may be formally undecidable. It's the same story with looking at different cases of rule or different rules. Is there any case that does this or any rule that does it? What's remarkable to me, even after 40 years of ruleology, is how many surprises there end up being. You have some particular kind of rule, and it looks as if it's only going to behave in some particular way. But no, eventually you find a case where it does something completely different and unexpected. And yes, this is in effect computational irreducibility reaching into what one's seeing. Sometimes I've thought of ruleology as being at first a bit like natural history. You're exploring the world of simple programs, finding what strange creatures exist in it and capturing them for study. And yes, in actual biological natural history, the diversity of what one sees is presumably at its core exactly the same computational phenomenon that we see in abstract ruleology. So how does ruleology relate to complexity? It's a core part, and in fact, the most fundamental part of studying the foundations of complexity. Ruleology is like studying complexity at its ultimate source, and about seeing just how complexity is generated from its simplest origins. Ruleology is what builds raw material and intuition for making models. It's also what shows us what's possible in the computational universe and what we can use to model and understand the systems we study. In metamodeling, we're going from models that have been constructed and drilling down to see what's underneath them. In ruleology, we're in a sense going the other way, building up from the minimal foundations to see what can happen. In some ways, ruleology is like natural science. It's taking the computational universe as an abstracted analog of nature and studying how things work in it. But in other ways, ruleology is something more generative than natural science, because within the science itself, it's thinking not only about what is, but also about what can abstractly be generated. Ruleology in some ways starts as an experimental science and in some ways is abstract and theoretical from the beginning. It's experimental because it's often concerned with just running simple programs and seeing what they do. And in general, computational irreducibility suggests you often can't do better. But it's abstract and theoretical in the sense that what's being run is not some actual thing in the natural world with all its details and approximations, but something completely precise, defined, and computational. Like natural science, ruleology starts from observations, but then builds up to theories and principles. Long ago, I found a simple classification of cellular automata, starting from random initial conditions, somehow reminiscent of identifying solids, liquids, and gases, or different kingdoms of organisms. But beyond such classifications, there are also much broader principles, with the most important, I believe, being the principle of computational equivalence. The everyday course of doing ruleology doesn't require engaging directly with the whole principle of computational equivalence. But throughout ruleology, the principle is crucial in guiding intuition and having an idea of what to expect. And by the way, it's from ruleology that we get evidence like the universality of Rule 110 and of the 2-3 Turing machine for the broad validity of the principle. I've been doing ruleology, though not by that name, for 40 years, and I've done a lot of it. In fact, it's probably been my top methodology in everything I've done in science. It's what's led me to understand the origins of complexity, first in cellular automata. It's what's led me to formulate the general ideas in a new kind of science, and it's what gave me the intuition and impetus to launch our new physics project. I find Ruleology deeply elegant and satisfying. There's something very aesthetic, at least to me, about the purity of just seeing what simple rules do. And it doesn't hurt that they often make very pleasing images. It's also satisfying when one can go from so little and get so much, and do so automatically just by running something on a computer. And as well, I like the fundamental permanence of Ruleology. If one's dealing with the simplest rules of some type, they're going to be foundational not only now, but forever. It's like simple mathematical constructs, like the icosahedron. There were icosahedral dice in ancient Egypt, but when we find them today, their shapes still seem completely modern, because the icosahedron is something fundamental and timeless, just like the Rule 30 pattern or countless other discoveries in Ruleology. In a sense, perhaps one of the biggest surprises was that Ruleology is such a comparatively new activity. But as I catalog in a new kind of science, it has precursors going back hundreds and perhaps thousands of years. But without the whole paradigm of a new kind of science, there wasn't a context to understand why Ruleology is so significant. So what constitutes a good piece of Ruleology? I think it's all about simplicity and minimality. The best Ruleology happens after metamodeling is finished, and one's really dealing with the simplest, most minimal class of rules of some particular type. In my efforts to do Ruleology, for example, in a new kind of science, I like to be able to explain the rules I'm using just by an explicit diagram, if possible, with no words needed. Then it's important to show what the rules do as explicitly as possible. Sometimes, as in cellular automata, there's a very obvious visual representation that can be used. But in other cases, it's important to do the work to find some scheme for visualization that's as explicit as possible and that both shows the whole of what's going on and doesn't introduce distracting or arbitrary additional elements. It's amazing how often in doing Ruleology, I'll end up making an array of thumbnail images of how certain rules behave. And again, the explicitness of this is important. Yes, one often wants to do various kinds of filtering, say of rules, but in the end, I've found that one needs to just look at what happens, because that's the only way to successfully notice the unexpected and to get a sense of the irreducible complexity of what's out there in the computational universe of possible rules. When I see papers that report what amounts to Ruleology, I always like it when there are explicit pictures. I'm disappointed if all I see are formal definitions or plots with curves on them. It's an inevitable consequence of computational irreducibility that in doing good Ruleology, one has to look at things more explicitly. One of the great things about Ruleology as a field of study is how easy it is to explore new territory. The computational universe contains an infinite number of possible rules, and even among ones that one might consider simple, there are inevitably astronomically many on any human scale. But okay, if one explores some particular Ruleological system, what of it? It's a bit like chemistry, where one explores properties of some particular molecule. Exploring some particular class of rules, you may be lucky enough to come upon some new phenomenon or understand some new general principle, but what you'll be doing is systematically adding to the body of knowledge in Ruleology. Why is that important? For a start, Ruleology is what provides the raw material for making models, so you're in effect creating a template for some potential future model. In addition, when it comes to technology, an important approach that I've discussed and used quite extensively involves mining the computational universe for technologically useful programs, and good Ruleology is crucial in helping to make that feasible. It's a bit like creating technology in the physical universe. It was crucial, for example, that good physics and chemistry have been done on liquid crystals, because that's what allowed them to be identified and used in making displays. Beyond its pragmatic value for models and technology, another thing Ruleology does is to provide empirical raw material for making broader theories about the computational universe. When I discovered the principle of computational equivalence, it was as a result of several years of detailed Ruleology on particular types of rules. And good Ruleology is what prepares and catalogs examples from which theoretical advances can be made. It's worth mentioning that there's a certain tendency to want to nail down Ruleology using, for example, mathematics. And sometimes it's possible to derive a nice summary of Ruleological results using, say, some piece of discrete mathematics. but it's remarkable how quickly the mathematics tends to get out of hand, and even a very simple rule having behavior that can only be captured by huge amounts of obscure mathematics. But of course, in a sense, that's just computational irreducibility rearing its head and showing that mathematics is not the methodology to use, and that instead something new is needed, which is precisely where Ruleology comes in. I've spent many years defining the character and subject matter of what I'm now calling Ruleology, but there's something else I've done too, which is to build a large tower of practical technology for actually doing Ruleology. It's taken more than 40 years to build up what's now the full-scale computational language that is the Wolfram language, but all that time I was using what we were building to do Ruleology. The Wolfram language is great and important for many things, but when it comes to Ruleology, it's simply a perfect fit. Of course, it's got lots of relevant built-in features like visualization, graph manipulation, etc., as well as immediate support for systems like cellular automata, substitution systems, and Turing machines. But what's even more important is that its fundamental symbolic structure gives it an explicit way to represent and run essentially any computational rule. In doing practical Ruleological explorations, and for example, searching the computational universe, it's also useful to have immediate support for things like parallel computation. But another crucial aspect of the Wolfram language for doing practical Ruleology is the concept of notebooks and computable documents. Notebooks let one organize both the process of research and the presentation of its results. I've been accumulating research notebooks about Ruleology for more than 30 years now, with textual notes, images of behavior, and code, and it's a great thing. Because of the stability of the Wolfram language and its notebook format means that I can immediately go back to something I did 30 years ago, run the code, and build on it. And when it comes to presenting results, I can do it as a computational essay created in a notebook in which the task of exposition is shared between text, pictures, and computational language code. In a traditional technical paper based on the mathematical paradigm, the formal part of the presentation will normally use mathematical notation. But for Ruleology, as for computational X fields, what one needs instead is computational notation, or rather computational language, which is exactly what the Wolfram language provides. And in a good piece of Ruleology and Ruleology presentation, the notation should be simple, clear, and elegant. Because it's in computational language, it's not just something people read, it's also something that can immediately be executed or integrated somewhere else. What should the future of Ruleology be? It's a huge, wide open field in which there are many careers to be made and an immense number of papers and theses and books that can be written that will build up a body of knowledge that advances not just the pure basic science of the computational universe, but also all the science and technology that flows from it. Philosophy and the foundations of complexity. How should the phenomenon of complexity affect one's worldview and one's general view of thinking, way of thinking about things? It's a bit of a roller coaster-like ride. When first confronted with complexity in a system, one might think there doesn't seem to be any science to that. But then with great effort, it may turn out to be possible to drill down and find the underlying rules for the system, and perhaps they'll even be quite simple. And at that point, we might think, okay, science has got this one, we've solved it. But that ignores computational irreducibility. And computational irreducibility implies that even though we may know the underlying rules, that doesn't mean we can necessarily scientifically predict what the system will do. Instead, it may take an irreducible amount of computational work to figure it out. Yes, you may have a model that correctly captures the underlying rules for a system and even explains the overall complexity and the behavior of the system, but that absolutely does not mean that you can successfully make specific predictions about what the system will do, because computational irreducibility gets in the way, essentially eating away the power of science from the inside as an inevitable formal fact about how systems based on the computational paradigm typically behave. But in a sense, even the very phenomenon of computational irreducibility, and even more so, the principle of computational equivalence, give us ways to reason and think about things. It's a bit like in evolutionary biology or in economics, where there are principles that don't specifically define predictions, but do give us ways to reason and think about things. So what are some conceptual and philosophical consequences of computational irreducibility? One thing it does is to explain ubiquitous apparent randomness in the world and say why it must happen, or at least must be perceived to happen by computationally bounded observers like us. Another thing it does is to tell us something about the perception of free will. Even if the underlying rules for systems, such as us humans, are deterministic, there can be an inevitable layer of computational irreducibility, which makes the system still seem to be to a computationally bounded observer to be free. Metamodeling and Ruleology are in effect extensions of traditional science needed to handle the phenomenon of complexity. But what about extensions to philosophy? For that, one must think not about the phenomenology of complexity, but really about its foundations. And that's where I think one inevitably runs into the whole computational paradigm with all its intellectual implications. So yes, there's a philosophy of complexity, but it's really the philosophy of the computational paradigm. I started to explore this towards the end of a new kind of science, but there's much more to be done, and it's yet something else that can be reached by serious study of the foundations of complexity. Multi-computation and the surprise return of reducibility. Computational irreducibility is a very strong phenomenon that in a sense pervades the computational universe. But within computational irreducibility, there must always be pockets or slices of computational reducibility, aspects of a system that are amenable to a reduced description. And for example, in doing Ruleology, part of the effort is to catalog the computational reducibility one finds. But in typical Ruleology, or for example, a random sampling of the computational universe of possible programs, computational reducibility is at best a scattered phenomenon. It's not something one can count on seeing. But there's something confusing about this when it comes to thinking about our universe and our experience of it. Because perhaps the most striking fact about our universe, and indeed the one that leads to the possibility of what we normally call science, is that there's order in what happens in it. Yet even if the universe ultimately operates at the lowest level according to simple rules, we might expect that at our level, all we would see is rampant computational irreducibility. But in our recent physics project, there's been a big surprise. Because with the structure of the models we used, it seemed that within all that computational irreducibility, we were always seeing certain slices of reducibility that turn out to correspond to the major known laws of physics, general relativity, and quantum mechanics. A more careful examination showed that what was picking out this computational reducibility was really the combination of two things. First, a certain general structure to the underlying model, and second, certain rather general features of us as observers of the system. In the usual computational paradigm, one imagined rules that are successively applied to determine how the state of a system should evolve in time. But our physics project needed a new paradigm that I've recently called the multi-computational paradigm, in which there can be many possible states of the system evolving in effect on many different interwoven threads of time. In the computational paradigm, one can always identify the particular state reached after a certain amount of evolution. But in the multi-computational paradigm, it takes an observer to define how a perceived state should be extracted from all the possible threads of time. In the multi-computational paradigm, the actual evolution on all threads of time will show all sorts of computational irreducibility. But somehow what an observer like us perceives has smoothed out all of that. And what's left is something that's a reflection of the core structure of the underlying multi-computational rules. And that turns out to show a certain emergent set of physics-like laws. It's all an important piece of metamodeling. We started from a model intended to capture fundamental physics, but we've been able to drill down to find the essential primitive structure underneath, which turns out to be the idea of multi-computation. And wherever multi-computational occurs, we can expect that there will be computational reducibility and emergent physics-like laws, at least for certain kinds of observers. So how does this relate to complexity? Well, when systems fundamentally follow the computational paradigm with standard computational models, they'll tend to show computational irreducibility and complexity. But if instead they follow the multi-computational paradigm, then there'll be emergent laws to discover in them. There are all sorts of fields like economics, linguistics, molecular biology, immunology, etc., where I've recently come to suspect that there may be good multi-computational models to be made. And in these fields, yes, there will be complexity to them. These fields, yes, there will be complexity to be seen, but the multi-computational paradigm suggests that there will also be definite regularities and emergent laws. So in a sense, from within complexity, there will inexorably emerge a certain simplicity, so that if one observes the right things, one can potentially find what amounts to ordinary scientific laws. It's a curious twist in the story of complexity, and one that I, for one, did not see coming. Back in the early 1980s, when I was first working on complexity, I used to talk about finding scientific laws of complexity. And at some level, computational irreducibility and the principle of computational equivalence are very general such laws that were at first very surprising to see. But what we've discovered is that in the multi-computational paradigm, there's another surprise. Complexity can produce simplicity, but not just any simplicity, simplicity that specifically follows physics-like laws, and that for a variety of fields might indeed give us something we could consider to be scientific laws of complexity. What should happen now? It's a wonderful thing to see something go from just an idea to a whole developed ecosystem in the world. But that's what's happened over the past 40 years with the concept of doing science around the phenomenon of complexity. And over that time, countless workflows associated with particular applications have been developed, and there's been all sorts of activity in all sorts of areas. But now I think it's time to take stock of what's been achieved and see what might be possible going forward. I myself have not been much involved in the daily work of the complexity field since my early efforts in the 1980s. And perhaps that distance makes it easier to see what lies ahead. For yes, by now there's plenty of understanding of how to apply complexity-inspired methodology and computational models in particular areas. But the great opportunity is to turbocharge all this by focusing again on the foundations of complexity and bringing the basic science that arises from that to bear on all the various applications whose workflows have now been defined. But what is that basic science? Its great symptom is complexity, but there's much more to it than that. It's heavily based on the computational paradigm, and it's full of deep and powerful ideas and methods. And I've been thinking about it for more than 40 years, but it's only very recently, particularly based on what I've learned from our physics project, that I think I see with true clarity just how that science should be defined and pursued. First, there's what I'm here calling metamodeling, going from specific models constructed for particular applications and working out what the underlying more minimal and more general models are. And second, there's what I'm calling ruleology, the study of what possible rules or possible programs in the computational universe do. Metamodeling is a kind of meta-analog of science, probably the most directly related to activities like computational language design. Ruleology is a pure basic science, a bit like pure mathematics, but based on a very different methodology. In both metamodeling and ruleology, there is much of great value to do. And even after more than 40 years of pursuing what I'm now calling ruleology, I feel as if I've only just started scratching the surface of what's possible. Applications under the banner of complexity will come and go as different fields and their objectives ebb and flow. But both metamodeling and ruleology have a certain purity and clear anchoring to intellectual bedrock. And so we can expect that whatever is discovered there will, like the discoveries of pure mathematics, be part of the permanent corpus of theoretical knowledge. Hovering over all of this, all of what we might study around complexity, is the phenomenon of computational irreducibility. But within that irreducibility are pockets and slices of reducibility, and informed by our physics project, we now know that multi-computational systems can be expected to expose observers like us what amounts to physics-like laws, in effect leveraging the phenomenon of complexity to deliver accessible scientific laws. Complexity is a field that fundamentally rests on the computational paradigm. In a sense, when we see complexity, what is really happening is that some lump of irreducible computation is being exposed. So at its core, the study of complexity is a study of irreducible computation. It's computation whose details are irreducibly hard to find out, but which we can reason about, and which, for example, we can also use for technology. Even 40 years ago, the fundamental origin of complexity still seemed like a complete mystery, a great secret of nature. But now, through the computational paradigm, I think we have a clear notion of where complexity fundamentally comes from. And by leveraging the basic science of the computational universe, and what I'm now calling metamodeling and ruleology, there's a tremendous opportunity that now exists to dramatically advance everything that's been done under the banner of complexity. The first phase of complexity is complete. the ecosystem is built, the applications are identified, the workflows are defined, and now it's time to return to the foundations of complexity and to take the powerful basic science that lies there to define complexity 2.0 and to deliver on the amazing potential that the concept of studying complexity has for science. Well, that's the end of the piece that I've written about charting a course for complexity. So now I'd be happy to have a discussion, take questions, comments on all of this. Okay. Okay, let's see. It's a question about the relation between constructor theory and ruleology. Constructor theory, I don't necessarily claim to understand with great clarity, but it's a theory that's arisen from thinking about quantum processes and thinking about kind of how one actually sees things happen in quantum processes rather than reducing it all to information. It kind of thinks about kind of the physicality of information as primary and the information content as secondary. Now, I think what we've found is that constructor theory actually corresponds very much to a way of interpreting these kind of multi-way systems that arise in our physics model and in our way of thinking about quantum mechanics. Basically, I think what happens is in our model of physics, there's this notion that there are many possible threads of history that branch and merge and form this whole multi-way graph that we study a lot. I think that constructor theory is a way of approximating that multi-way graph by thinking about not what we tend to do in the physics project, the evolution of that multi-way graph in time and the many possible reference frames that you can pick that correspond to essentially different quantum observations. It's a way of kind of approximating the multi-way graph by going more in one step to get to results. But beyond that, I can't say. And we've been meaning to do a discussion with folks from constructor theory for a while in our attempted to be weekly sort of Q&A with other people. So hopefully we'll get a chance to do that soon, and then we'll hear in more detail about constructor theory. It's a question from David. Are the rules that define physics fundamentally less complex than the axioms of Peano arithmetic? That's an interesting question. So here's what I increasingly think. I think that in a sense, there are infinite number of possible rules that can be used as the underpinning for physics. We as observers are sampling certain features of the consequences of those rules. When that sampling always gives us, in a sense, the same results, but the details of those results depend in detail on how we are sampling things. So in a sense, we get the physics that our methods of observation allow us to see. And the underlying rule is just the thing that kind of initiates driving the whole process. So here's a way to think about it. If you think about, for example, the dynamics of molecules in a gas, we know that the detailed interaction laws for molecules in the gas don't affect things when we kind of zoom out and look at the overall fluid dynamics of the gas. And so it is, I think, with physics, that the kinds of things that we observe as the kinds of observers that we are do not depend on the details of which particularly one of a large class of rules we use. Now, there's much complexity to that statement, and it all revolves around this very abstract creature that I'm calling the rulead, which is this kind of limit of the entangled evolution of all possible rules. But that means that in a sense, physics can be based on essentially anything that is capable of doing computation, anything that is, for example, computational universal. So in a sense, that's the foundation of physics. You can say, for us as observers, what is the convenient rule to attribute the behavior of the universe to? And that we might hold up and say, look, we found the law of the universe, and it allows us to make predictions that we, being the kinds of observers we are, can readily try and explore. Okay, so now we look at mathematics. Okay, so Peano arithmetic, the axioms of arithmetic, things that say that x plus y equals y plus x, that have the induction axiom, things like that. Okay, so here's a strange fact about Peano arithmetic. Peano arithmetic is universal in the sense that it is in principle possible to encode in Peano arithmetic any computation. And moreover, in principle, we can encode within that computation, we can encode any other area of mathematics. So we could encode geometry. We could even encode any computation, like the computations we use to make a fundamental theory of physics. So within Peano arithmetic, we can encode all of those computations, just as within some fundamental rule that we attribute to the universe, we can encode a whole range of possible computations. So in a sense, and that's exactly what the principle of computational equivalence suggests, there is equivalence between the computational sophistication of the rules of Peano arithmetic and the computational sophistication of the rules that govern our universe. In a sense, those things are exactly equivalent. Now, if we start to ask which ones are convenient for our observation of these systems, well, that is an interesting question. So the rules, the axioms that we give for Peano arithmetic are ones that take the general possibility of what can exist in any computational system and specialize it for our particular way of thinking about arithmetic, our particular way of constructing numbers and so on. Now, even in Peano arithmetic, one of the things that's complicated is, while we might think that Peano arithmetic is a thing that describes integers and addition and things like that, it's a consequence of Gödel's theorem that any finite set of axioms for Peano arithmetic allows things that aren't just the ordinary integers. It allows bizarre non-standard arithmetic. It allows all these kinds of wild things that are possible given those axioms, but don't correspond to our intuitive notion of integers. So we could pick other axioms that have all kinds of extra things and different things to say about that wild stuff that isn't related to our normal notion of integers. But in a sense, what we're doing when we pick the Peano axioms is we're picking a set of axioms that accord with our everyday intuition about numbers and arithmetic and things like that. A bit like in physics, the observer who is doing the math and thinking about numbers and so on has something of a choice in the axioms they pick. And the ones that we might pick normally in Peano arithmetic don't happen to have these things that to us look like things that bring in only these very complicated, wild kinds of non-standard arithmetic. So as a practical matter, it is a really interesting question whether our view as mathematical observers leads us to a more or less complicated, sort of most obvious kind of set of rules for arithmetic, or whether the corresponding thing as a physical observer leads us to a more or less complicated set of rules for the universe. I don't know the answer to that. My guess is that Peano arithmetic is a bit more complicated than it needs to be. And it is probably the case that it's almost certainly the case that the axioms that we currently know for Peano arithmetic are not the simplest ones you could use. But they may be ones where they have a particularly direct representation of things like addition and numbers and so on. There may be some other axiom system that you could use, but to even describe addition, you have to build that up out of a lot of pieces within that axiom system. The same happens, let's say, with group theory. Okay, the normal axioms of group theory, based on how we normally think about group theory, have a group multiplication operation, they have an inverse operation, etc. But there are simpler axioms for group theory, even a single axiom that one can pick for group theory. But the operation that it has in it is some kind of bizarre division operation. It's not the everyday kind of, yes, we recognize this from thinking about math operations that exist in sort of the most standard axioms of group theory. So there's often a trade-off, which we don't understand completely well at this point, between kind of the amount of effort the observer is prepared to go from their notion, whatever it might be, whatever it might historically have developed about this thing, and what the actual description based on these models looks like. But it's a really interesting question how that trade-off works, and I don't think we know yet quite how to fit that together. Jonas asks, what's the difference between rule systems and algorithmic generators like pseudo-random number generators? There isn't any difference. Pseudo-random number generators are a good example of rule-based systems. So for example, a very common kind of primitive version of a pseudo-random generator is something like linear congruential generators, where you're just successively multiplying by a number and reducing mod another number. And actually, it turns out that if you do multiplication by 3 mod 6, for example, the thing you'll get out is, 3 in base 6, multiplication by 3 in base 6. The thing where you look at the pattern of digits that you get out is actually, for example, a cellular automaton. And for example, sort of conversely, the Rule 30 cellular automaton that I've studied so much as a matter of ruleology, so to speak, also happens to serve as a very good pseudo-random number generator. We used it in Wolfram language for 30 years or so. So yeah, it's very much the same kind of thing. You can think about ruleology as being a sort of a minimalist, principled study of things that might be used as pseudo-random generators. There are plenty of ruleological systems that where you say, well, it's kind of random, but it has some obvious regularity to it, and where it would be like a total fail as a pseudo-random generator, but it's a very interesting piece of ruleology. Okay, there's a question from Mark. What does the formalism for describing observers and foliations look like? How are observers and foliations described in the formalism for multi-computation? That is a very good question, and one that I have personally been spending a considerable amount of effort thinking about, and I don't have a great answer yet. Let's talk about the analogous case in general relativity. Basically, what you're asking is, what are convenient coordinate systems, convenient kinds of reference frames in general relativity? And we know a few: inertial frames. That's one example. We know things like the Schwarzschild solution, the Kerr solution, solutions to the Einstein equations that correspond to black holes, things like that. Those are places where we've kind of nailed down the way that we label and structure and foliate space-time. But the general question of what's the general way to think about foliation, that's the thing that I'm currently thinking about. By the way, you see the same kind of issue in, if you think about traversal order for even a tree, you've still got the same kinds of things. Is it breadth first? Is it depth first? Is it leftmost, innermost? These are all essentially questions about how you're turning what in the tree as a partial order into a total order. A foliation is weaker than a total order because it's just looking at slices of things. A total order asks you to visit every particular thing in turn. But these same issues about sort of how do we parameterize, is it a breadth first, is it a depth first, whatever search. I think what is needed there is a language for describing foliations. And that language is also a language for essentially describing metrics in general relativity, for search strategies. It's a language for describing how you sort of sample a multi-threaded, multi-computational system. And I'm thinking about it, and I think it's a very interesting question. And if people have suggestions about it, I'd be really interested. I would say that there are a little bit of mild assistance from higher category theory, although it's more in the structure than in the details of how to do this. I think there are formalisms, whether it's pi calculus or various kinds of process algebra kinds of things that you might think would be helpful, but I have not yet managed to see how they are helpful. I think it is something where it is just as when we invent things like Turing machines that sort of idealize the process of computation, what we are trying to do here is to invent something that somehow idealizes the process of observation. And I think what we will end up with is probably sort of a Turing machine-like idea for how to do this parameterization, and maybe many different ideas for parameterization that one will then show are equivalent, but different ones in different cases may seem like the more natural ones to be thinking about. And actually that analogy is an interesting one, which had not occurred to me before. That's what one has to search for. What is the kind of Turing machine of describing foliations and so on? There's a question from Michael. How is computational irreducibility and Kolmogorov complexity related? So, okay, Chaitin-Kolmogorov complexity, the big idea is that you assign complexity based on the minimal program necessary to describe the thing you have. So most of what we're talking about in Ruleology is a story of low Chaitin-Kolmogorov complexity stuff. The rules are small, yet what they produce is something which, at least to us, looks complicated. In terms of kind of Chaitin-Kolmogorov complexity, those things are not complex. Those things are simple because they have simple rules. They can be described by a simple program. The thing that has been a long-running discussion between myself and Greg Chaitin has been, is the universe really like omega, a thing with high algorithmic complexity, or something like pi, which has a simple algorithm to compute it, yet its digits, once computed, seem kind of random? Well, so computational irreducibility is a story of what it takes to make things. It is not a story of what rules it takes to seed the making of those things. In a sense, computational irreducibility is the thing that is, it is something where what you start from is a thing of low algorithmic complexity. Computational irreducibility is a thing you build up that is somehow has an irreducible content, even though at some level, the algorithmic rules from which it came are very small and simple. So it's the irreducible thing, not the original rules. In algorithmic complexity theory, it's the original rules that are the big and irreducible thing that is comparable in size to the object itself. Whereas in computational irreducibility, it is this process of evolution that might be incompressible, not the rules by which it's made. Okay, there's a question from Senri. How does probability fit into all of this? So Ruleology is mostly about, here's a rule, what does it do? You can obviously have an overlay of saying, let me look at a big ensemble of possible rules and say, what's the chance that one of these rules does this or that? That's a perfectly reasonable thing to do. It may turn out to be the case that there are places where the analysis of that ensemble of rules is easier than the analysis of individual rules. It's not clear, but that's kind of how probability enters. In kind of the pure science of Ruleology, one doesn't want to think about probabilistic rules. At least that's not how I imagine things. And what is the reason for that? The reason is that, in a sense, when one says, when one is modeling something, when one says, well, that's probabilistic, that's to us just something random. What one's saying is one's model is not complete. There's something outside the system that's kind of kicking it with some probabilistic way, with some kind of extra randomness. Ruleology is about saying, let's do the minimal thing. Let's look at the whole everything. Let's look at a rule that describes everything and see what consequences that has. And as I say, one could then go in and sort of either break up the time evolution of what happens and say, on average, there is a black cell half the time or something like this. Or one can say, let's look at an ensemble of possible rules, an ensemble of possible initial conditions, and do probability kinds of calculations there. Now, it can often be the case that you might say, well, if I just make it probabilistic, it's going to be easier because it's going to wash everything out. It's not hard to see that even probabilities can be computationally irreducible or undecidable. Even to know what's the precise probability for something to happen, there may be all of these sort of tails of possibilities that can kick over that probability, even just the probability, not just the specifics of what will happen in a particular place. Memes asks, do you fear this paradigm may take some of the fun out of life? It's funny because I have had this point of view that I will just follow the science where the science goes. I have personal ideologies of various kinds and personal things I like about life and the world and so on. And I've sort of tried to, in a sense, run these as two parallel tracks. I'm going to see where the science goes, and I'm going to have my own personal views. And if it turns out those things agree, great. If it turns out they disagree, so be it. One of the things that I find life interesting. I find the kind of, I like to think the things we do have some meaning. I like to think, I also find people interesting. I don't, even if I can deconstruct everything about people to some set of computational rules, I personally, as a personal matter, find people interesting and enjoy people, so to speak. So how does this all fit together? Well, for a while, I thought it absolutely didn't fit together. And I thought that the science that I was doing had sort of deconstructed everything. And in a sense, as you kind of imply, taken the fun out of everything. It's like, okay, the universe is just made from the set of simple rules and everything we do. And it's kind of like, I can have these little visions as I kind of walk along saying, no, I'm just updating pieces of hypergraphs. And, I move my hand and it's just occupying a new set of atoms of space and everything is being rewritten. And there's 10 to the 100 operations going on that are causing the motion of my finger from here to there and all that kind of thing. I suppose one should be flattered that the universe is going to so much trouble to produce these things that we sense, so to speak. But actually, there's a different point of view that I've realized, that computational irreducibility, while it makes us not as confident about science, it makes us not say about science, as we have tended to say for the last 300 or so years, science has it. Once we've scienceized it, we can just figure out everything about what's going to happen. Computational irreducibility says that isn't true, that even when it is scienceized, even when there's an underlying model for something, it can still be irreducibly difficult to work out what will happen. And actually, I think that's a pretty good message in terms of our lives and existence for the following reason. If you could figure out what the answer will be, you can say, what is the result of life, the universe, and everything? It's just 42, so to speak. We can jump ahead and get to the answer without living the time to get to that answer, without living our life through time. And in a sense, that's a rather unsatisfying belief, that it's like all the things that happen in history and in our lives and so on, it's just like you can just calculate the end result of history will be X. If that was the case, it feels very empty to live through that history, but it's not the case. Instead, there's this phenomenon of computational irreducibility, and computational irreducibility tells you that what is happening to us now is something that is irreducibly hard to compute. The effort that we go into computing the things, or that the universe goes into on our behalf computing these things, that effort that it's going to is the effort that is needed to do that computation. There's no faster shortcut, some better universe out there that could just say, hey, universe, I can just tell you what's going to happen in the end. It's this. So in a sense, computational irreducibility, to me, it has very interesting kind of multiply edged consequence. It both shows us that the passage of time is something meaningful. There is something achieved by the passage of time. It's not just, oh, tomorrow is a new day, and it's at a different point in the coordinates of time. Instead, tomorrow is a day computed irreducibly and inexorably from today. And it doesn't happen except by that computation. That computation is the process of it happening, and that computation is something irreducible. So that's kind of the good news, it's meaningful. The bad news is, if we want to say we're going to wheel in science, and science is going to tell us the answer to everything, this is telling one that isn't the case. It's not going to work. Science is no more capable of working out what will happen than we are capable of saying, you don't need to live that piece of life. We just know what the outcome is going to be. So in a sense, what science is doing, what we're being told is we're being given a certain humility about science that says, yes, there are things that science can do. And by the way, you never want to give up on science, because when there is computational irreducibility, there are always an infinite number of possible pockets and slices of computational reducibility. So even though the whole story may be computationally irreducible, that doesn't mean that there aren't places where you can jump ahead. And by the way, those places where you can jump ahead represent the inventions and discoveries and so on that we make use of in leading our lives. So in a sense, there's always places to jump ahead. It's always worth doing science because there are always inventions and discoveries to make. But don't imagine that science is just going to nail it all and say, and the answer is X, because computational irreducibility says that won't happen. And that's a good thing because it tells us that the time that we live through is time that has some meaning. On the other hand, it's a bad thing in the sense that it doesn't allow us to say, hey, look, this is what we know is going to happen. It doesn't allow us to control the world by basically saying, let's move this lever this way because we know that the consequence of that is this. It's kind of an everyday realization that there are always unintended consequences. There's always bugs. There's always things where you can't foresee what will happen. That's not just a matter of anecdotal observation. It's a matter of scientific fact at this point, that we can see that even in these very simple models of what's going on, there is this computational irreducibility, which gives us this certain sort of humility about science. It's interesting perhaps to sort of reflect on what this means in terms of the history of philosophy and people's discussion about sort of the role of science, even the role of religion in connection with these kinds of things, what it is that we can know, what it is that is beyond what we can know, and should we imagine that, how do we think about what we can know and what we can't know? And to me, it's, I had not expected this. I have to say, I went for a decade or more believing that what I had done was to sort of deconstruct kind of all the things that I might value about kind of leading one's life were scientifically somewhat deconstructed, that even though I might personally like these things, that at some level, if I really were to drill down and look at the science, it was all sort of a bit empty. But it turns out it's not true. It turns out that the science actually tells one it's not empty. It's actually something where there is something irreducible. There's an irreducible thing inside, and that's what it means to go through time and live our lives. So somewhat to my surprise, this expectation that this kind of what it means for sort of one's everyday conception of things has landed more in the direction that I sort of would have the personal prejudice it should than I expected, even though I think in the doing of science, and it's a very important principle in the doing of science, the extent to which you separate the doing of science and the conclusions of science from the things that you might imagine based on your sort of personal preferences and personal what you personally like in the world. Let's see. RJ is asking, what might it look like in practice to use Ruleology research about complexity to solve a commercially technological problem? So we've been doing this a whole bunch. You want to find a good random number generator? Just go search the computational universe, do good Ruleology, understand what's out there in the computational universe, and wheel in the good random number generator. We've done the same kind of thing for all kinds of things in various kinds of feature detection areas and so on. Machine learning is, in a sense, a very hairy version of Ruleology, very, very hairy, probably unbelievably unnecessarily hairy. But we don't yet know that, in the sense that machine learning just says, consider these programs out there that are constructed with all these layers of neural nets. We're going to gradually sort of try and get ones that do the kinds of things we want. The big discovery about the computational universe, the sort of core of Ruleology in a sense, is it doesn't take very complicated rules to get very rich behavior. And that means that if you want to find something that's useful for some technological purpose, it could be a very simple rule, and you could end up just doing an exhaustive search. And we've done that many times. I mean, there's a bunch of core things to do with collisionless hash codes, a bunch of other things, which just in our technology stack just work using essentially what I would now call Ruleological principles. So it's that's what that would kind of look like. Now, another place where you might look for that is in things like molecular computing, where you say just what kind of rules might you need on a molecule to be able to support molecular computing? What is the phenomenology of this kind of molecular process? And then how do we map that into the things that we care about, that we want to actually do computing about? That's another kind of thing. But essentially what it is it's a little bit like it's what happens a little bit in things like drug discovery. It's like you have a giant library of possible compounds, and when you have some theory about what you want, some target that you want to deal with in medicine, you say, let me take my giant library of chemicals and let me just try running it, try seeing whether this chemical has this effect on this type of cell or whatever else it is. And so it will be with Ruleology, that essentially one has these big, I mean, we've done this a bunch, you have this thing with 1 trillion different possible rules, and you say, let me run these rules against some objective that I have and see whether any of them succeed in bringing in what I need. That's the kind of methodology one should think about. And so to organize those libraries in chemistry, there would be, the big pharma companies, for example, are very proud of their sort of libraries that they can use to try and test different kinds of molecules against particular targets that one's identified or thought worthwhile. So there's a question from Dougie. This is about reversibility of rules. How about we take this question to tomorrow when I'm going to talk about the physics project? I think this is getting us deep into quite things about the physics project, but I'm happy to address that. That's an interesting suggestion from Crucial Flow, saying, I recommend blog reading live stream display the blog text in the future. That is a good idea. Obviously I was reading this text, but I wasn't sharing the screen where I was reading it. This is experiment number 1 of this process. And I realized as I was doing it that another feature is I have a much better microphone for reading podcasts, and we weren't using that, and that was goofy. But that's a good suggestion. That's much more interesting to see that than to see me yakking about it, at least as the full screen. Mikhail, does this mean that math and computational approaches are trying to solve the same thing, but math does it top down and computation does it bottom up? Well, just yesterday I spent many hours working on metamathematics, and I think I'm not ready to fully answer that question yet. Give me another month or so, then I can answer that question. RBS. I have 2 questions. Computational language, does it have an instruction set, a manual or something? Yeah, I mean, our computational language, this is Wolfram language. You can go look on the web or on desktops. And yes, it absolutely has an instruction set. It has about, these days, about 7,000 built-in primitives. We're still a bit less than the number of common words in the English language, although our primitives, I think, are rather richer than words in the English language. But it used to be the case back, more like 30 years ago, I was writing a physical book that described our computational language, Mathematica, as it was then referred to as. Over time, by the time we got to version 5, the book had expanded to be quite big, and by the time it got to version 6, it just blew up, and the book would have been 20,000 pages long. Now I think the book will be 200,000 pages long. So obviously all that stuff is to be found online. So that's the story of our computational language. Is Ruleology a new field? How can one contribute to it? Okay, well, I kind of started doing this back in the 1980s, and other people have started doing it too. We've just been inventorying kind of papers that are essentially contributions to Ruleology. The name Ruleology is a new name. I've been meaning to come up with a name for decades. It's a name to describe this area of exploring the computational universe of simple programs and seeing how they work. Can people contribute to it? Absolutely. It is a wonderful field to contribute to because it is a field that, in a sense, doesn't require the kind of depth. It does not have a giant tower of knowledge that's been built in, let's say, pure mathematics that requires, 10 years of study to get to the point of being able to do it. It's a thing where people who have certain kinds of skills and a certain turn of mind can contribute clean, great, elegant ruleology without that vast background of knowledge. Now, in another 50 years, ruleology will have a whole big, bolus of actual corpus of actual knowledge, and to contribute to ruleology in 50 years' time will no doubt require knowing a bunch of stuff that's there right now. It already does to some extent. I mean, if you're studying simple cellular automata, there's a huge amount that's known about those. I've worked on those a lot, and so have a lot of other people. And it's like, well, if you don't want to do the same thing somebody already did, there's a certain amount to know. But in fact, we intend to create a thing we're calling the Ruleological Society, which is going to be a platform to help sort of concentrate the things that have been done around the world in what amount to ruleology. It's really a fascinating situation. I mean, if one's interested in the history of science, it's really an interesting situation, because back in the early 1980s, I kind of first started doing these things. A whole bunch of people got involved. They were mostly at the time were kind of young, unsituated scientists. And they enjoyed doing this kind of thing, as I have greatly enjoyed doing it. And they wrote papers, and the papers were strewn across a zillion kinds of journals, from electrical engineering to pure mathematics, to complexity, to sometimes physics, to other areas. Sometimes they had to kind of hide their ruleology in an appendix to a paper that was actually supposed to be an economics paper or something. Well, now the ruleologists can come out, so to speak. There's enough of them, and there's a big enough sort of corpus of knowledge and understanding about what to do that it's something that we can really make as a coherent thing, and it's something that is, I think, when one creates a field. I was going to say, and as a new field, it has this fascinating feature that there are people who started doing it in the 1980s, who in many cases have ascended to the point where they're quite senior in whatever the core field that they did was. So we have a very fascinating platform today for ruleology, which is not just people who are sort of just entering the field or just entering science, but it has not been a thing that it's been sort of an underground field for a long time. And so I think it is now time to bring it to the foreground. And I think we now have sort of the, that's one of the things I hope to do is over the next little while, sort of bring ruleology to the foreground, because I think it is in some sense, perhaps even the most fundamental basic science. I mean, you can ask, what is the most fundamental basic science? Is it physics? Is it pure mathematics? Is it computer science? What is it? I think I could make a very credible argument that it's ruleology and not any of those things, especially from what we now know about physics. Of course, when you want to do a particular kind of activity, then ruleology may be far away as an abstraction of what you're actually trying to do. Now, in terms of contributing to it, there's a question of what makes, so in terms of, I mean, in a sense, I've built Wolfram language as, if nothing else, and it has many, many other uses, it is a fantastic platform for doing ruleology. And there is nothing even vaguely comparable to it. And, so that is, it's kind of, that's a place to start. And I think that it's really a question of what constitutes, a good piece of ruleology, the elegant kind of drilling down to the simple program, seeing what it does, coming up with definitive results. Those are the essence of good ruleology, so to speak. And it's what I hope we will be helping to define as we go forward here. And it's absolutely a thing to which there are many contributions to be made. It's an area that has the feature that its incremental contributions are valuable. There are other fields where incremental contributions are really going to be washed away with time. You know, you make an incremental contribution to a field which is continuously churning its basic theories or continuously churning its prejudices, and what you've done will be just like, oh, well, yes, that was a thing, but nobody cares about that anymore, or it isn't a thing where you're building putting another brick into this giant structure. But Ruleology is of that kind. And the things that, just like in pure mathematics, the things that were done in the 1800s, we've pretty much mined most of them today. A few still left unmined, but even the ones that are unmined to now, people still say that's mineable. We expect that will be mined in the future. And so it will be with Ruleology, that the things that are done in the 2020s of Ruleology will be forever things which are solid things that can be mined 100 years from now or whatever else. So I think it's a great field. And it also has the feature that it is a field to which there can be non-professional contributors. I think it's important to maintain the kind of the culture and methodology of the field. And it is all too easy to just sort of say, oh, I'll just run some random cellular automaton and here's a picture of it. There's more to it than that. There's what's the essence of what's going on? What's the simplest example? What can you say about it that is kind of a thought bite about an intellectual unit that is simple, so to speak. That's something that there's a methodology of that is something people who learn to do professional science, if they learn professional science well, they probably learn that methodology of sort of finding the essence of things and being able to express it. But that's something that is a feature. It's a feature of good writing. It's a feature of many things. It's not unique. That kind of meta methodology is not unique to science. And so Ruleology is something that can be practiced by people who have that kind of methodological turn of mind without necessarily the stack of knowledge of any particular existing science. And I think it's a fascinatingly level playing field for contributions. Okay. Let's see. Aaron, how would one recommend onboarding oneself and finding a reasonable workflow for working in Ruleology? Is working with multi-way graphs and physics project materials the best starting point? Multi-way graphs are great. They are not the simplest entry point for Ruleology. I would say the NKS book, the New Kind of Science book, is a really good place to start. But in terms of the methodology, actually our summer schools, there have been some lectures given at our summer schools that are pretty good starting points. And I'm pretty sure those are online and we should collect those together. And thank you for the implicit suggestion. I have to say that I'm sort of being led, and the questions people are asking here are encouraging it more, that I should probably write an introduction to Ruleology text that should be pretty easy for me to write. I've been doing this stuff for 40 years and it's all about finding the sort of essential essence of what's going on. So surely I can do that in describing the field itself. But the core methodology, I mean, is pick your favorite kind of system. You can absolutely pick multi-way systems. They're a little bit complicated relative to other things because they're a little bit hard to visualize, and they're a little bit floppy in terms of kind of things which come naturally to us. When you have a cellular automaton, it's an array of cells, they just go down the page. When you have a multi-way system, it's a graph of possible time evolutions, and it's a bit more difficult to see what's going on. Just as a pure matter of the impedance match between, well, at least a human like me and how the system behaves. That is not to say that there aren't other humans out there for whom multi-way graphs are tremendously, easily, naturally assimilable. For me, it's like, even though I've worked with them quite a bit, it's still much more of a struggle for me to sort of understand what's going on in a complicated graph than it is to understand what's going on in this kind of array of black and white cells, so to speak. But I would say that the methodology is you're creating notebooks. You can find endless examples of those in the working materials from the physics project, probably even ones from things I've done just literally last night are probably already online. It's really a question of the way I tend to do it is I'm doing experiments, I'm writing notes in the notebook about what's going on, I'm sometimes summarizing, and then I'm just progressing with figuring out, oh, this thing happens, that thing happens, maybe here I do a search for, can I find a thing that works this way? Here, maybe I will dig in and try and say, is that mathematically understandable? Can I use traditional mathematical methods to see what's going on here? Those are the types of things. And in the end, I'm building up a kind of notebook that is a representation of the research that I'm doing. And then I can kind of abstract from that to write a description of what there is to say. Let's see. Stephen Shepard is asking, I'm interested in real-world consequences of complexity, like the complexity of production processes. How can we measure complexity across a wide range of systems? Is that something that I think is already answered? You know, complexity is very much in the eye of the beholder. In some sense, you call something complex when you can't see what's going to happen. And the question of to what extent you can see what's going to happen depends on the methods you have to see what's going to happen. Computational irreducibility says that there is some universality to the things that are hard to predict. But there are many details. It's like compression algorithms. You know, you can say, I've got this image and I'm going to use JPEG compression, and it's a lossy compression. And how much can it compress this image? That's kind of the true information content of this image. But how much I can compress depends on what kinds of losses I'm prepared to accept. Depends on whether, you know, it's like, I don't notice the fact that that picture is different. But if I were a mantis shrimp, I would be big time upset about the reduction of the color palette of that picture or something. In other words, so it depends a bit on the eye of the beholder. I tend to think that let's assign a number to, like, the complexity of this thing is X, the complexity of that thing is 2X or something. I tend to think that that sort of misses the point of what we've discovered about computational irreducibility and so on. I think that's a sort of attempt to mathematicize kind of what is not really, doesn't really fit well into the mathematical paradigm. Now, having said that, we can start asking questions about, well, I think one has to reel back. You know, you talk about production processes. I'm actually kind of wondering, there are, I'm assuming you mean practical production processes like in a factory, not what are called production rules in the theory of term rewriting systems, which have little to do with factories. But let's assume you mean actual factory type production type things. And I suppose it's an interesting question. I've not really thought about this. You know, if you say, how do you describe what's happening in the factory? And in a sense, if you were writing a piece of computational language code to describe it, how long would that code be? That's more a kind of algorithmic complexity measure of, you know, what is the length of description that you give, not kind of if you were growing the factory, what would be the sort of the minimal thing to use. Now, I suppose one might also ask, given that I'm manufacturing this object, what is the minimal set of operations I can do to manufacture this object? You know, in sort of design for manufacturability, you might say kind of, you know, could I just have a chopping tool or a tool that slices things? And could I always go from this block of material down to the thing I want just by having that one operation and applying it in all these different ways? Those are interesting questions. I haven't really thought about those in terms of sort of how do you classify, you know, given this output that you want from your factory, what is the minimal set of operations that can achieve that output? That's an interesting question. And I think one of the things to say about that is that one of the big discoveries is just because it looks complicated doesn't mean it's complicated to make. You know, nature is a great example of a place where lots of things that look complicated were made by nature by just following the same simple rules over and over again. And one wonders how that relates to things like manufacturing. One wonders the extent to which it's possible to just say, I've got one machine, just keep running it over and over again. It kind of reminds me of knitting machines and the fact that people, as a slightly different thing, but people have programmed endlessly knitting machines to do cellular automata, where right down there at the level of the Jacquard loom-like thing, the rules of the cellular automaton are being applied. So right in the machine, it is generating the output. And what's interesting about that is, for example, you can end up with a piece of fabric that just keeps going and keeps changing and keeps giving new surprising things forever. It never repeats. It's not a pattern in the sense of being a repeating, I drew this pattern and now I make copies of it kind of pattern. It's something that is a rule-driven kind of piece object that is being produced. And you could kind of drive those rules right down to the level of the final sort of edge manufacturing of that device. Let's see. Cedric is asking, do I think that 4 dimensions of space-time is a significant number, and do I think that that number is somehow burnt into the laws of physics? I think the answer is going to be no. I think that number is not fundamental. I think that I think that's a particularity of our universe and our observation of the universe. The one thing that I think is a little bit more special is that there's only one dimension of time. I think that intrinsically there are many threads of time and in effect many dimensions of time, but the critical fact is that we human observers, as a feature of a very core part of our consciousness, we sequentialize time. We believe that there is a past that we remember, a future that's going to happen, and we have the notion that there is one thing happening at a given moment. We put our attention to one thing at a time. We have this single one-dimensional thread of time that we imagine the universe progresses according to. And so I do think that that's a fundamental feature of maybe not our universe, because I think our universe has this multiple threads of time and so on, but our parsing, our interpretation, our sampling of the universe. And in fact, that sequentialization of time is the thing that drives a whole lot of the kind of the dynamics that lead us to laws of physics that we actually observe. Let's see, Mark is asking, is there a way to have a follow-up conversation about this? Well, if people like this, please give us feedback, and happy to do that. We are, about the specific topic of Ruleology, we intend this platform to provide a whole variety of means of interaction between people. Okay, Mikhail asking, where is the low-hanging fruit in all this stuff? It's a shocking thing. The most simple cellular automata with nearest neighbor rules and black and white cells, there are 256 of them. I think I personally know most of them. Even there, I regularly find new stuff I've never seen before. Even in that, I've been looking at these things for 40 years. There are a limited number of them, but there's just tons of low-hanging fruit. And I would say that in terms of if you go beyond that and you say, well, let me look at cellular automata that have that depend on neighbors that aren't just nearest neighbors, but let's say we make those neighbors be one step away on each side, as opposed to just next adjacent. That stuff, the analog of the elementary cellular automata, as I called them. I think some people sometimes call these things Wolfram automata, which is nice since I've spent so much of my life working on them. But in any case, these sort of simplest cellular automata, even if you make that small change, you end up with something that just hasn't been studied. And what could you study there? Well, you may find, for example, let's say you're looking for, I don't know, nested patterns. There are particular kinds of nested patterns that occur in one case. What kinds of nested patterns can occur? There's some bizarrely different kinds of nested patterns that can occur even in the elementary case, cellular automaton case. Now, that would be just one of a zillion different things you could study. Another thing you might study is, what regularities do exist between these rules. For example, are there rules where the behavior is the same when you kind of separate that that cell one more step away, or are there, or does that always produce completely different behavior? I mean, I could sit here and generate these questions for at a high rate of speed. I actually wrote, when the New Kind of Science book came out, I actually started writing a set of open questions, and I didn't finish through, I would say through lack of energy and lack of immediate feedback. Years later, I discovered there were a few people who'd read them. One of them was Jonathan Gorard, who's been a critical contributor to our physics project, who read them when he was an early high school student and said that was sort of his favorite piece, and what a shame I didn't go on with those questions. So we might have had our physics project a decade earlier if those questions had continued to the point where it was talking about physics and the younger Jonathan had latched onto them. Who's to know? But it's really interesting to hear. I do appreciate people's comments here, because we're really trying to define how can we help to kind of. I think Ruleology is an area. It's actually much easier to get into than core questions in the physics project, because in the physics project there's both more, I would say, more difficulty in wrapping one's brain around things. Things are more abstract, and there's also many aspects of what has to be done there require serious knowledge of what's already been done in physics and mathematics and mathematical physics. Because in a sense, the physics project, insofar as it's being very successful, it's leveraging just all this work that's been done, particularly over the last century in mathematical physics. And if one doesn't know all that work, one's at something of a disadvantage. There are still questions that one can explore, but core Ruleology is explorable without that giant stack of knowledge of things like mathematical physics. And it's great to hear people ask these questions about sort of on-ramping, and we should think about those some more. And that's I think what you're kind of encouraging me to do is to just write down a zillion kind of questions that one might ask. And there are just so many. Another good place to look is at our summer schools. You'll find the projects done at our summer schools and summer camps over the last 20 years. There are many what amount to Ruleological projects that have been done, particularly in the earlier years, and then again very recently. And those are other kinds of raw material for suggestions about directions to go. As well as the Complex Systems Journal has published many kind of Ruleological studies over the course of time. Okay, Jay says, are there cross-disciplinary findings you would expect Ruleology to uncover soon? Well, I mean, that's an interesting question. Is it a cross-disciplinary field? It's probably more cross-disciplinary than pure mathematics. So the question is, are there places where things will be discovered in Ruleology that will immediately fertilize existing areas? I would say that the place where I'm most enthusiastic about that right now is in this multi-computation area and things to do with multi-way systems and so on. And I think that there's just it's kind of crazy. In fact, there are all these fields. Okay, so back when I was working on complexity, New Kind of Science, things like that, there were fields that were blocked because there's a big lump of complexity in these fields, and it's like nobody knows even where this complexity comes from. Now I think we know that, but now there are fields where they're blocked because nobody knows, is there an overall law? Is there a physics-like set of laws for these fields? And nobody knows. And this multi-computational approach is giving one a new way to think about that, a new way to expect sort of overall physics-like laws in economics, in linguistics, in machine learning, in neuroscience, lots of different areas. I've written about this recently in a piece about multi-computation. The real thing, though, is what we are learning is that insofar as you can use multi-computational models in these systems, they will have certain detailed consequences. The question is, when we make an observation in those systems, are the things that we observe, are the features of economics that we observe ones that are aligned with that sort of low-level ruleological behavior or not? In other words, it turns out in the physics case that things that we observe about the structure of space and time and so on are sort of are aligned with things that we can readily see, sort of how they emerge from the underlying ruleology. We need to understand, we need a theory of the observer, just as we need a theory of computation, which we now have, and we now have a good way to attack that with ruleology. We need a theory of the observer as well. And that's a piece of, as I was saying before, that's something that is much less well developed. I will not advertise that as being a simple problem. I mean, maybe it is a simple problem, and I'm just not smart enough to see it. But to me, I've been thinking about that problem in different guises for more than 40 years now. And, you know, I have to say, when it comes to these, quotes, difficult problems, my number one observation about difficult problems is, once you actually have the problem in your crosshairs, once you actually know what the problem is, you have a tremendous advantage. And I think now, with much more clarity, we understand what the problem is associated with the description of foliations, what observers are like, those kinds of things. Back in the past, I was thinking about things about evaluation fronts in evaluation in computational processes and things like that. And it was like, well, that's an interesting thing to think about, but it didn't really quite have the connections that it's now starting to have for me. And so I think that's as I say, you know, maybe it's easy now. Maybe there's some piece of really clear thinking that will allow one to make kind of the Turing machine of the representation of the observer. I haven't seen that yet. That is kind of another stage. Ruleology, as we can do it now, is something that has things to contribute, sort of here and now, Turing machines, cellular automata, register machines, substitution systems, multi-way systems, et cetera, et cetera, et cetera. The whole zoo, you can find a bunch of them in chapters 3, 4, and 5 of the New Kind of Science book. They're basically just a big catalog of all these different kinds of meta model to the end, simple models, simple computational models of things. And it's now a question of exploring those and providing the right ecosystem to kind of capture all that knowledge. I mean, I feel a bit like, and I need to study more of the history, it's a little bit like chemistry in the late 1800s, when people were like, let's study that molecule, let's study this molecule. Oh, by the way, that molecule is super useful because it's going to give us, you know, an antiseptic something or other, or it's going to be useful for making plastic or something else. But before we've studied those molecules for their own sake, we never get to the point where we can make those kinds of technological conclusions. All right, we should wrap up here. Thanks very much. That was a very interesting, and you're effectively making very interesting suggestions. And actually, we'd be happy to hear from you. We hope to have sort of more to say about specifically ruleology going forward. We will also be having a discussion about the field of complexity, hopefully with some people who have been involved in the creation of complexity institutes and so on. We're having that in a few weeks. I'm really keen to see the kind of big infrastructure that's been built, the big ecosystem that's been built around the banner of complexity, which I think in some ways has, I won't say lost its way, but it is not as energetic as I think it could be. And I think there can be a really big piece of leverage that exists from sort of doing more on the foundations of complexity. And that's something that I'm hoping to have a bit of a discussion about with people. All right, well, thanks very much. Thanks for joining us. And bye for now. Tomorrow I will be doing a Q&A about the physics project. So look forward to seeing you another